And then, of course, once you've made that reminder on your phones, you'll put your phones away, and I know about how long it should take you to do that. And okay, hey, my favorite student, good old Anne. So on your written section, you can certainly expect some nuclear equations. Now, how can I tell that this isn't alpha or beta or gamma decay? Because that's not an alpha or a beta or a gamma particle or ray. It's a neutron. So this is either fusion or fission. You know what? Actually, when a big atom splits into smaller ones, that's which one? Fusion or fission? It is fission. Okay? You get 1 mark for that. And then you're going to get 1 mark for filling in the blank. The way we'll do that is half mark off for each mistake you make, but otherwise you get 1 out of 1. What's the blank going to be? Well, I have to realize that on the left-hand side, I have a total of 1 plus 236 masses, a mass of 236. On the right-hand side, I have 143 minus and 90. I must have 3 masses left, and because each neutron weighs 1, I need 3 neutrons. 1 mark for that. It's usually 3 neutrons. I mentioned in the when we split the atom. Not always. It turns out there are situations where you can give off 2 neutrons or 4 neutrons, but generally, in fact, most of the video animations that I saw you, Alex, you noticed there was 3 neutrons coming off when the atom split. We're good, Matt? How do I know fusion? First of all, I know it's not an alpha or a beta or a gamma, so it's not decay. How do I know fusion? Small atom joining into small or small-ish atoms. I'm not splitting something. What about the mass? Well, on the left-hand side, I have a mass of 2. On the right-hand side, I have a mass of 4. You know what? I'm missing a mass of 2. What about the bottom? Well, here I have a total of 2 protons. Here I have 1 proton. I have a charge of 1. Now that I know that, Andrea, that means it's element number 1, which means I can tell you it's a hydrogen. So 1 mark for circling fusion, and then if you got this right, 1 out of 1, otherwise a half mark off for each thing that's wrong. So if you got the 2 wrong, half off, or the 1 wrong, half off, or the H wrong, half off. Yep.
Is the first question 2 marks?
Oh, sorry. Okay, here we go. C, fusion or fission? I think we're splitting into 2 medium-sized atoms. We're splitting it up. Does anybody come up with a good way to keep straight the words fusion and fission, what they mean? Someone had the S's thing, and that was okay, but problem is fusion also has an S, right? What are the blanks? Well, on the right-hand side, I have a mass of 90 and 143, and careful, not 1. What's the mass of this grand total? 3. So on the right-hand side, I have 90 plus 143 plus 3. On the left-hand side, I better have a mass of 236. I have a mass of 1 with the neutron right there. So you know what? This is going to be 235. What about my charges, my protons? Well, I got 37 and 55 and 0. Did I really need to add the 0? By the way, technically, and 3 times 0, because it's 3 neutrons, but Joseph, will that make any difference? I'll point it out, though, for what it's worth. On the right-hand side, I got 92. On the left, I better have 92. I got a 0. This is going to be a 92. Is element 92 uranium? This is and we, by the way, we would pronounce this uranium-235. If you were writing it out in English, you would write uranium-235, because that's the mass. By the way, also, another question I could ask, how many neutrons does this have? How could you calculate it? 235 minus 92. Are you cluing in? A calculator would be handy. Okay. Oh, Julie, 1 mark. and then a half mark off for each mistake for a total of 2. Here, oh, big atom. We fixed the typo, right? We said this isn't cesium, this is uranium. My bad, sorry, oops. I was cutting and pasting in a hurry, apparently. Not that it makes a difference to the other blank. It's still going to be 236 on the left. I got 236, take away 106, take away 3 times 1. 3 neutrons. Is the mass 127, is that right? And then the charge is going to be 92, take away 39. It's going to be element 53. What is element 53? I tried to make these somewhat realistic. Sorry? Iodine. Radioactive iodine. And this is fission. Half-life questions. What I tried to teach you is when you're doing half-life, go loopy. Okay? So this asks how many grams are left after 3 half-lives. How many half-lives? It's going to look like this. 1, 2, 3 half-lives. We're starting with 120 grams. 1 half-life will be how much left over? 60, then 30, then, hey, you know what? If you're good at your dividing and timesing by 2, you might be able to do this without a calculator. 15 grams. 1 mark. Oh, no, 2 marks. Okay. 2 out of 2 if you got the 15. Otherwise, I'd probably go, if you showed the work and have the wrong answer, I'd still give you 1 mark for going loopy. How many grams? Oh, and always make sure you read whether they're talking about the parent or the daughter, because the daughter is what's left, is what's turning into. Anyways, how many grams of the parent isotope are left after 96 years? Well, I need to figure out how many half-lives that is. Let's go loopy. There's 1 half-life. Now, I could label it 1, 2, 3 like in the previous question, or I could label it with how many years. 1 half-life is 24 years. I put it there because if you put it, are you asking, did you put it somewhere else? Don't put it there. You're going to get the wrong answer. You're counting the bumps instead of the gaps. That's what you might get the right answer as long as you're consistent on your mistake, but it's too easy to make mistakes. I put the half-life there and the products there. So the next 48 years, right? 24 more. 72? 96. You know what? It's 4 half-lives. I know it's 5 bumps, but it's 4 half-lives. Yep.
Why did you start at 24?
What's 1 half-life? How many years? Okay, because they gave me this in years, they didn't want me to do 96 half-lives. 96 years. Okay, if they give it to me in years, instead of just counting half-lives, I'll put the amount of time each half-life is worth. Okay, and we started with 120, so it's going to be 60, 30, 15, you know what, 7.5. Now, Matt, if you got 7.5 grams as your answer, I'll give you 2 out of 2, but I'm trying very hard to help kids keep straight. What are we counting, Mr. Dueck? And the answer is your products are appearing on the bumps, but the half-life, the time goes on the loops. Go loopy for half-life. That's how many grams of the parent are left. What's C asking me? How many grams of the daughter are left? Now, it's the same amount of time. Well, you know what? We started with 120. 7.5 is still left from the parent. So 112.5 must be the daughter. Is that right? Yeah? By the way, if I make a sloppy math mistake, let me know, because I am doing math in my head and I'm on cold medication, so who knows. 2 marks. Turn the page. The half-life of Rabalkium is 7 days. Pretty close to his dating life. No, never mind. I took that back. Here we go. Oh, that was a good glare there. You know what? We could actually make these dating questions, because that's sort of a half. Anyways, okay. What fraction? Well, you could sort of treat dating as decay. For some people, trust me, I've seen some people. Anyways, half-life is 7 days of Rabalkium. What fraction of a sample? Okay, now they want a fraction. After, Matt, how many days? Careful. In part A, how many days? Okay, do I know how many half-lives that is? Now, Conlon, you may say, hey, Dueck, I know that's 2 half-lives, and great. But if not, you can go loopy. There's 1 half-life of 7 days. There is another 14 days. It's 2 half-lives, 2 loops. If they want what fraction is left, what do we start with? 1. And then the next fraction would be a half. And the next fraction would be what? Quarter. 1/4 will be left. 3/4 has turned into the daughter. 1/4 has turned into, is still remaining from the parent. And you can see, Cam, if you analyze, for example, rock samples and you know how much of one element or the other is, you can work your way backwards and figure out how old stuff is. This is how we do radioactive dating. What fraction will remain after 35? Oh, by the way, instead of what fraction, I could have asked for what percent. 1 divided by 4 times 100. There, 25%. I figure if you can do one, Andrea, you can do the other. What fraction will remain after 35 days? Well, you may say, I know it's 5 half-lives, but Courtney, if you can't see it, it's going to be 7, 14, 21, 28, 35, and quit. What fraction? 1, a half, a quarter, keep going. 1/8, keep going. 1/16, keep going. 1/3, you know what? 1/32 is going to be left. 1/32. 2 marks. Oh, there you go. I did say you could do it with dating. Carbon dating. Carbon dating? Oh. Okay, tough audience. Can you give yourself a score on this quiz, please, out of 18? Chapter 7 quiz. Did I put somewhere for you guys to write your name on it? Oh yeah, there is somewhere to write your name on it. Here we go, good old Anne. You know what? I've had enough of Anne. How about Ima? Good old Ima Chekhov. Here we go. Which of the following is true of subatomic particles in a nucleus of vanadium-50? Of vanadium what? So even though it has a mass of 51, normally we have an isotope. What's the mass of our isotope? 50. I'm not going to use 51. I'm going to use 50. This is an isotope. So it has 23 protons. That's correct, that's wrong, because it's still element number 23. But the number of neutrons is not 28, 27. And this is why on the periodic table that a lot of the masses have decimals, because it's an average mass. Some of them are isotopes, some of them aren't. So number 1A. Number 2, which of the following nuclear, did I unpause? I did, didn't I? Can't remember. Yeah. Which of the following represents alpha decay? No. Yes. Yes. No. They love to give you these chart kind of questions, Ty, on the provincial. The best way to do it, don't even look down at the answers yet. Cross out which ones you know are wrong in the chart, and then you kind of scroll your eyes down and zoom out, and clearly the answer is B. B. Consider the following partly completed nuclear decay equation. What would correctly complete this? A 7 down there, because I got a 6 and I got a -1. It's got to add to 6. Do I need to go any further? Well, but as soon as I got that 7, it can only be D. One of the things on provincials, and you guys got 3 of them this year, you want to get in the habit, Alex, anytime you write anything, you always glance at the multiple choice answers, and you're going to find on a lot of the questions, you can quit. On the old Math 12 provincial, which we don't offer anymore, on fully 1/3 of the questions, you would only have to get halfway through solving, and you could cross off wrong answers as you went along, and you could quit. I would teach my kids that. It would save them about half an hour on the provincial, which is gold. I mean, that means you can make a major mistake and still recover and have extra time. Good habit to develop.
How long were
They were 2.5 hours. 2 hours, 2.5 hours.
How long does it take to road?
How long does it take? You have to stay for an hour. What you're really asking is, how long does it take to do well? Because the short answer is, for you guys, they're multiple choice. How long does it take to color in 60 squares randomly?
Yeah.
Well, 60 seconds. But they're designed to be finished in about 90 minutes, but you're allowed to stay up to 3 hours. Okay?
Well, you say you have to stay there for a minimum of 1 hour.
Well, you're not allowed to let anybody out for an hour.
Oh.
Okay? That's for security reasons, because believe it or not, you could memorize the questions, text them to a friend of yours in the interior who was maybe running 5 minutes behind and their school hadn't started the exam yet, and now he would have some questions. It's a pretty secure process. For example, if your cell phone rings during the test, we have to give you a 0, so we'll be yelling at you all come June to leave your cell phones powered off or at the front of the room or at home, because our big fear is, how do you guys tell what time it is? I look at a watch. Most of you guys look at your phones, so we're worried. We're worried that during the exam, a kid will innocently glance at their phone to see what time it is. We have to give them the 0. It's clear we're not allowed to give any judgment or anything. We have to assume you cheated and give you a 0. It's very strict. The exams have to be kept behind 3 locked doors until we bring them out, and inside a safe. There's a whole procedure. Can I keep going though? Good. Here we go. Refer to the common isotope pairs, I don't have a copy here, to find the maximum effective dating range for carbon-14 dating. Okay, the common isotope pairs is this bad boy here. Well, you know what? The half-life is 5,730 years. That's not the best range, though, because I can still take half of a quarter. Let me see what we got for answers here. Definitely no. Definitely no. I can do better than that. I'm leaning towards D. I'm not a big fan of that question.
I don't get that.
Okay?
Don't be-
So, you ready? Here's why. Let's suppose we have, I'm going to pick a nice number, 100 grams of a substance. Here's one half-life. How many years is one half-life? 5,760. That's from the chart, right? I can still measure 50 grams or 50% pretty easily. That's still within our detectable level. I could also go another half-life. Can someone go 5,760 times 2 for me, please? Anybody, quickly?
Although it's awesome.
Can anybody go 5,760 times 2, please? But I need to get this. Yeah.
10,520.
10,000? I think it's 11,000, isn't it?
Oh, sorry, 11,000.
11,520. Now, that would give us 25% left, which we can still detect. Can someone go 5,760 times 3, please? Anyone? It's cutting into your homework. And that's 12.5. We can still detect 12.5%. In fact, it's only when we get to around 50,000 years total that there's so little left that we can't detect it. Now, that's what this question is asking, and I think it's phrased badly. Excuse me. So here's what it says. I'll read the question again. Refer to your formula sheet. To determine the maximum effective dating range for carbon-14. Carbon-14 is effective up to about 50,000 years. And I did say that in our notes, if you go back and check in the notes, give or take. And that's what it's asking. Now, having said that, remind me, and I'm going to make that a bonus question, but not right now, at the end when we score them up.
Well, why did you write 5,760?
Oh, it's 5,730?
Yeah.
Is that what it is? Thank you, Julie. So, fix all those, but still the principle holds, yeah? Coughing again. I was doing so good. Hang on. Pause. Okay. Refer to your formula sheet, number 5, to determine the age of a sample of rock that contains equal amounts of uranium-235 and lead-205. If I go and look at this, it turns out uranium-235 decays into lead, is it 205 or 207? 207, I read it wrong. It decays into lead-207. So they are a daughter-parent pair, a parent-daughter pair. If they're equal amounts, how many half-lives has gone by if I got a 50% left? Just one. How long is one half-life from your purple sheet? Sorry? 710 million years? So if you had a sample of rock and it had 50% uranium and 50% lead-207, that rock is around 710 million years old. Is that okay, Courtney? Yeah? Good. Potassium-40 has a half-life of 1.3 billion years. How old is a rock that is found to contain 1 gram of potassium-40 and 3 grams of argon-50? Okay, here's my first question. How many grams of the original material was there? How many grams of the original material was there? 4. Not how much do I have now? What do we start with? 4 grams. So you ready? 4 grams. Half-life. How much would be left after 1 half-life? 2. How much would be left after 2 half-lives? Ding, 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 ding. So the first question is, how many half-lives old is this rock? How many loops did I draw, Julia? What's 1 half-life? 1.3 billion years. Another 1.3 billion years. You know what? It's 2.6 billion years old. That gives you an idea, Conlon, of some of the ways we can kind of mix and match half-life questions. If you don't panic, they're not too bad. Keeping in mind, I'm not a big fan of number 4. Hey, nuclear. Which of the following correctly completes the following nuclear equation? You know what? The fact that Mr. Dueck changed B and C probably means one of those two is the right answer. Otherwise, he wouldn't have bothered changing them. Right? Yes. Is it B? Let me see. Oh, someone says C. Let's see. On the left, I got a mass of 236. On the right, I got 143 and 3 neutrons. So 3 times 1, 90. Oh, you know what? I'm done. It's the only one it can be. I could keep going, Sage, but it's got to be a 90 up there, so why? That's the only one that fits. Mr. Dueck, you didn't tell us number 8. Yeah, I did. No, Mr. Dueck, you didn't tell us. The CANDU reactor is a nuclear reactor. It splits atoms. So really what you're looking at is saying, which of these 4 equations is splitting an atom? That's fusion. That's what goes on in the sun. That's alpha decay. What's A? It's combustion, right? Hydrocarbon plus oxygen gives carbon dioxide and water. You know what? It's got to be B. Oh, yeah. There's your fission. Got to be B. I kind of like that question, even though it's a little cheap, Taylor, because I'm for you know without knowing that you know, and I kind of like questions like that that force you to think a little bit and use a process of elimination. I think that's good test writing. What applies to the energy in the sun? It's not heavy, unstable nuclei. It is lightweight nuclei that join, and it doesn't produce stuff that's radioactive. This is why we think fusion is the future. It doesn't produce radioactive waste. B. Blah, blah, blah. Okay, what don't we have a good solution yet? Nuclear reactor might have a runaway chain reaction. We have good solutions for that. We have safety protocols in place. We're really not too worried about that. An awful lot has to go wrong. In Japan, it took one of the biggest earthquakes in the past 1,000 years. Pardon me? Well, we can build them in lead and surround them in lead. We're really not too worried about that. You can live next to a nuclear reactor and you're safe. You're fine.
This is more of like an opinion thing, though.
No.
Doesn't state that they're built in.
Our big issue is this right here, nuclear waste. Wait a minute. B, Mr. Dueck, says nuclear waste. You know what? If we bury the nuclear waste and we guard it, which we do, by the way, it's not that easily thiefable, stealable. There's the word I'm looking for. They're very heavily guarded, but it's still there. I'm going to end up making 10 a bonus as well, but it's good thinking. Now we get into more specific. Beta particle. H, yeah? It's got to be beta. Oh, sorry, beta particle, Mr. Dueck? Sorry, let's try that again. Beta particle is a fast-moving electron. F, scared you all. Gamma radiation, I guess A, because that's the only one that's actually radiation. Mass number, D, the sum of the number of protons and neutrons. Daughter isotope is the product, It's the, G, the newly formed nucleus. Fusion, combining small atoms into larger atoms. Is that B? And half-life, E. Is it FADGB? Is that right? 1 mark each. Short answer. How are these isotopes? So potassium-39 and potassium-40. How are they similar? What do they have in common? I'm going to give you a hint. They have the same number of protons, because that's how we define what an element is. You know what? I can't believe I wrote that out. P plus. Or you could do the other symbol, 1p1. Any other suggestions? Same element? Sure. But why are they the same element, Max? Same number of protons. How are they different? Different. Come back here. My eraser. Different number of what? Neutrons. N0 or 1N0, whichever symbol you want to use. Which one is heavier, potassium-30 or potassium-40? That's meant to be fairly obvious. Potassium-40. Potassium-40. Why? So you're saying it's heavier because it's heavier. That's called circular reasoning. Like saying, what? 1 extra neutron. I can even tell you, not just 1 extra, because the mass is up by 1. The typo is this one here. This one is yucky. 200 micrograms or 200 billionths of a gram. How much will be present after the following periods? So 1 half-life is 5,730, so 100. 14,600, I think it's supposed to be 11,600 or something like. Anyways, just skip that one. How much will be left after 4 half-lives? You ready? What are we starting with? 200. After 1 half-life, how much is left? After 2 half-lives, 3 half-lives, 4 half-lives. So it can be done kind of counting on your fingers, but Alex, you know what? When in doubt, go loopy. Because that's pretty easy as well. 200, 100, 50. Sorry, 200, 150, 25, 12.5. And again, Matt, the half-lives are the loops, not the bumps, because I know I've written 5 numbers. It's because you're starting with something. So what was it? 12.5? Provide the nuclear symbol for the parent nucleus. So if this has had alpha decay, that means it's lost a mass of 4. It was once 211, and it used to be 87. And 87 is element number francium. Beta decay. Beta decay, that means this used to be element number 93. It gained a proton. Used to have a mass of 239, but instead of Pu, oh, that's a great element,
What's the
It's-
bottom number on that?
Np. So it's 239, 93 Np. Gamma decay, oh, you know what? Nothing changed, it just lost energy. Okay. So, I made the written section up from your quizzes. I basically took the written section of the test, changed the numbers or the equations, and turned those into 3 separate quizzes. So ignoring the very last one, Sage, that I didn't count, but the first 3 quizzes that I did count for marks, that's a pretty good indication of the written section. What about the multiple choice section? Well, I tried to give you a bit of an idea of some of the stuff you might see, but on this very last quiz, Andrea, the one that I didn't count, but I'm not going to put any of the really cheap ones on there. There will be a couple, though, where you're going to have to, Jaden, reason your way or think your way by a process of elimination to the answer. I do kind of like those. I think those are good critical thinking. Like there was the one question on the can-do reactor where we said, look, I can figure out which one it is because it's got to be nuclear fission. I could cross out the 3 wrong equations, even though I didn't know which one was left. Okay? So what do you need to know how to do? Some key ideas. What can you tell me about an isotope? Isotopes have the same number of but different numbers of, what goes in the blank? Okay. This would also mean that they have different masses. Remember the notation that we had? So if you say, for example, potassium, good gosh, I can't make these up on the fly, I gotta look. So potassium 41 would have a mass of 41, even though most potassium atoms have a mass of 39. Okay? So make sure you understand the concept of isotopes. Make sure you can find the number of neutrons from any isotope if I give you the mass, and the mass is in the name. Make sure you understand the notation. What have we said for the notation? Symbol, mass, atomic number. So if you see something like NP 93 240, what element number is that? 240 or 93? Element number 93. How many protons does it have? How many protons does it have? 93. How many neutrons does it have? 240 minus 93, whatever the heck that is, 147 if my math is correct. Okay? So I would have no problem, for example, giving you stuff like fill in the blank. I would have no problem giving you something like, let's make one up, Mr. Dueck. Somebody at the door?
No.
Yeah. You just gotta speak up a little there, girl.
I didn't do that. He did that.
Okay. What goes in the box? More specific in this situation, what goes in the box? More specific in this question, what goes in the box? More specific in this particular question, what goes in the box? Symbol is what? Capital P, lowercase r. I think it's called praseodymium. Okay. Don't get them mixed up. It's make sure you understand what's what. Okay? Then you can definitely expect a bunch of decay equations. We've done a bunch of those. Sorry. I think you folks are doing pretty good. Key idea, the tops have to balance, the top numbers, and the bottom number. The masses have to balance. The charges have to balance. Just be careful for neutrons if there's a coefficient in front of the neutrons. Okay. One thing we didn't do, we did do in the homework, reading a decay curve. Something like this. Okay? I'll have no problem on the written or on the multiple choice giving you some kind of a decay curve. What's the half-life of this? Well, we're starting with 80 grams. What's half of 80 grams? 40 is right here, and if I read across, you know what? 40 grams occurs how many days in? The half-life would be 2 days. Okay? Half-life would be 2 days. And once I have that, I can continue to use the graph if I want to, or I can go loopy. I mean, either or is now an option. Okay? So, make sure you can read a decay curve. Vocabulary, there are, I think it's 16 vocab questions. Plus or minus a couple. There could be an isotope. Get it? Plus or minus? Oh, okay. Over the head. You're focused. This is really it's a cool unit, but it overlaps, each topic overlaps so much with the other topics. Jaden, it's not like I taught you a whole bunch of new stuff. This goes back to Julia's earliest comment. Once I showed you how to balance your first radioactive equation, Julia, the rest of them, the numbers just got bigger. But it's still, make sure the top balances. Make sure the bottom balances. And then the bottom is what tells you what symbols to put in. What symbols to put in. Let me give you a couple to practice from if you guys want. Oh, I don't want that. Oh, that's not what I want. I want textbook PDFs. There we go. Go to the very end, Mr. Dueck. This is a big chemistry review. We're not going to do that. So make sure you can handle. This is a unit review. I don't want a unit review. Yeah, I got you. Come on, you can do it. Unit summary. Here we go. So again, make sure you can handle these kinds of equations. Make sure you can handle these kinds of equations. Make sure you can handle these kinds of equations. If you can, you're in good shape. I might give you a chart, something like this to fill in. Again, probably I'd turn this into some kind of a multiple choice question because that's a lot of writing, but still. Lithium-7, what's its mass number? 7, because they told me. Even though when I look on my sheet, oh no, lithium normally does have a mass of 7. What's its atomic number? 3. How many neutrons? 4. What about neon-22? Now, normally, according to my sheet, neon has a mass of 20. That's what my pink periodic table says, but this one has a mass of 22. Still has an atomic number of 10, so neon 22 has 12 neutrons. It's probably unstable. It's going to decay. This has a mass of 29. What element number? 14. So what element is it? This is silicon 15. So as far as I'm concerned, again, Conlon, I can give you any of these two of these three numbers, and you can find the missing number, no problem, or symbol. I'm not going to have you draw Bohr models. I've done that already. I don't know. Anything else you're wondering about? Okay.